Okay, we are ready to start on Chapter 2. Hopefully you printed out the notes for Section 2.1 and are ready to follow along and fill them in with me. Notice it's just one page today. So let's get started with some definitions. We're going to be talking about increasing and decreasing functions here first, and also piecewise functions. So starting up here at the top, this first definition, if it rises as you go left to the right. So we have a function, and as we go to the left to the right, the graph goes up. That is an increasing function. So that's our first definition to fill in the blank. Now notice this definition also has the algebraic way of saying the same thing. So let me just draw in the x and y axis here. And I know this isn't perfect, but it will get the job done, I think. If you have two values of x, let's call them a and b, and such that a is smaller than b. That means b is on the right side of a. If you have these 2 points, then when you take the function, when you apply the function of that, that means you get the y value of a, which would be f of a. It is also going to be less than f of b, and you can see that right here. As you go up to the right, that should be a b right there. As you go up to the right, a is less than b, so f of a is less than f of b. So that's an algebraic way that you can check this without even drawing the graph. Okay, next one is just the opposite. A decreasing function drops as you go from left to right. So its general shape is going to be like this. And again, if you pick a point A that's less than B, this time when you take f of A, do you see how it is higher than f of B? So it goes down left to right. And that second part of these definitions just gives you a way to check these algebraically without having to draw the graph. Now we also have functions that don't do either. They don't increase or decrease, and those are called constant, which kind of makes sense. They just stay at the same height as you go left to right. In the last chapter, we talked about those horizontal lines and what the points on those horizontal lines look like. They all have the same y value, and so for any a and b, the y's are going to be the same. So you pick any a and b, those are our x values. When you take the function, if it's a constant function, the a and the f of a and f of b are the same. Okay, we also have functions that can be increasing at some points and decreasing at others. So here on this graph, I'm just going to draw a little graph there. That's a function. Notice for any x value, there is exactly one y. I might have kind of dipped back here a little bit. Pretend like that just keeps going out to the left. So you'll notice this increases in some sections. So this very first part over here is an increasing interval. And then it decreases for a while. I'm just going to abbreviate that DEC. And then over here, it increases again. So we talk about increasing functions. If that definition would mean it increases at all points, decreasing function would mean it decreases at all points of the graph. But then you have these graphs that are a combination where it increases on some intervals, and I should say increasing for this sentence. Okay, a function can be increasing on one interval and decreasing on another. Or it could also be constant at some points in there. So that's just an example of a function that has an increasing portion, actually two different sections that increase, and then one section that decreases. You can also have graphs that are much more disjoint. You can have something like this, and when you get up to this point, it drops down here to a point below, and then continues on. So this is something that you're going to be seeing. These are called a piecewise function, because there really is a section here where it changes. And a piecewise function also might have this curve over here. It might even have, let me make this a flat section, so a constant section, and then maybe a piece over here. And you might actually have a different formula for each one of those, a different algebraic function for each one of those. And so you're going to see this in the homework where it's going to list for all of the numbers less than 2, that means all of the x's less than 2, all of these over here. It might have f of x equals and then a formula, and then maybe from 2 up to 5, it's just f of x equals, looks like on this one, -2, and then maybe over here on the right, as we get to 5 and bigger, we have a linear function. And so that's your function is going to be listed something like this. And I don't have this curve. I just made that up a while ago. So I'm just going to call it x squared plus 4. It's probably not quite right, but it's some kind of, it looks kind of like a parabola, kind of like a quadratic formula. And that's for x less than 2. And I'll say or equal to. See how I have the dot filled in up here, but I have an open circle down here at the bottom. So I'm going to put or equal to. We follow that. And then we have f of x equals negative 2 for going from negative 2, not including, up to x, up to 5. So that's the section here that's flat. And then we have a linear function. And again, I don't have the formula for that worked out. I probably should have had a real example. Looks like it crosses maybe down here. And maybe the slope is about 1. So I'm going to say 1, 2, 3, 4, 5, 6, 7. I'll say x minus 7. Let's see, does that work out here? Negative 2, no, 5 minus 7. Yeah, so that works out here. 5 minus 7 would be negative 2 here. And so that's for all the points x. And I'll put greater than or equal to 5, even though this point right here is on both of those. So I could put the or equal to either place here. That breaks the graph up into these 3 sections. Okay, let's continue on. And let's just talk a little bit about minimums and maximums. A concept with graphing is that you can have a point that is the minimum of the whole graph or the maximum. So we see this, the classic example is the parabola. We've talked about parabolas before. That's the graph of a quadratic equation. There's a point that is, if it's a parabola that opens downward, so it comes to the vertex, or that highest point is a maximum. If the parabola opens upward, then you're going to have a minimum. But sometimes you have spots that are the minimum for a range or for an interval. And we saw this on the graph that we just drew. I'm going to change my color. For example, this point right here that is marked with red, that is a maximum. If you just take a section of the graph, like maybe from here, actually from here all the way down to here and all the way to the end, it's the highest point for this section, but then you can see over here to the right, it starts going up again and it actually goes past that point. So this is what's called a relative maximum. And then down here on the bottom, we have a relative minimum. So that's what we're going to fill in the blanks here in this next section. It looks like I need to scroll up so that you can see it. And I'm changing my ink color. Where's my scroll bar? There we go. Okay, is that on? Hold on, let me just check. I need to move this down so you can see where I'm at. Okay, so in this first blank is going to be relative. Let me see how it's worded. If there exists an open interval containing a C such that, okay, so these, it's fill in the blank, so I can say either one first. We'll talk about the relative minimum first. So relative minimum. Okay, on this graph we have one relative minimum right down here at the bottom. I just wrote that here, relative minimum. It exists if there is an open interval around it. So if you go to the left or right, in the immediate left and right, it doesn't mean you go all the way out into infinity, but there's an area there where that is the lowest point. So how do we say that algebraically? We say that there is a point C, so our C is our point here where we have our relative minimum, such that f of C is less than all of the f of x's, or all of those y values. So I'm not sure why that just suddenly jumped down there. All of the y values in that interval. Oops, I still had my eraser on. I'm getting better, guys, but it is practice. I did get a stylus that seems to be working better now. Okay, so relative minimum. Graphically, it means it's that lowest point in an interval, and algebraically, you would say that if you take the y value, or the f of C of that point, it's going to be smaller than the y values of all of those points on either side of it within that interval. And so we're just going to fill in the blanks down here for the relative maximum, same way, just the opposite. So the relative maximum there is an interval containing a point C such that f of c, what do we need to say this time? If we look up here at this red dot up here at the top, f of c is going to be higher than in the other. So the y value is greater than all of the f of x's in that interval. Okay, so I think the concept from the graph is pretty straightforward. Here we're just converting that into algebra because sometimes you're going to want to check if something's a relative min or max without actually graphing it. And so that's where we take our f of c and we say, okay, if I made x a little bigger and a little smaller, is my y value still less than those new y values? And if that's true, then it's a relative min. And for the max, the f of c, or the y value for c, has to be bigger than the y value for those points on either side of it. Okay, we're going to stop this video here. There is just one more little thing from this section that we're going to do, but if you need to take a quick break, go grab some water or maybe finish this up later, that's fine. When you come back, grab your graphing calculator because we're going to talk about how to use your calculator to find those relative mins, relative maxes, and also state the ranges in which the function is increasing and decreasing using your calculator.